Welcome to the next lecture on the course Descriptive Statistics with R software. You may recall that in the last lecture we started a discussion on measuring the association between two discrete variables on which the observations were obtained as numbers obtained by counting. And in that lecture we had discussed that from the given set of data we can create a table and a contingency table. From that contingency table we can obtain marginal frequency distribution and the conditional frequency distributions, and these marginal and frequency distributions can be obtained in terms of absolute frequency and relative frequency. And we had taken an example and we understood how these values are coming and we understood how to compute them manually. Now, in this lecture I will try to show you that these contingency tables can be obtained inside the R software. So, I will take an example and I will try to show you that how to obtain the contingency table, and after this I will introduce some measures, some quantitative measures to find out the magnitude of the association or the degree of association between the two variables. So, now first I try to take the topic that how to construct the contingency table in R software, right. So, as usual I will assume that we have got here a data vector, and suppose we have two data vectors x and y. You may recall that in the case of univariate frequency distribution, if I have the data vector as x, then we had used the command table to find out the frequency table, and when this table was divided by the length of x, then we had got the frequency table in terms of relative frequencies. Similar to that, when we want to tabulate the bivariate data, the same command is used, that is table, table. The only difference is that now inside the argument you have to give the two variables or two data vectors, and similarly if you have more than two you can express all those data vectors here separated by comma. So, this table xy is used to cross classify the factors to build a contingency table of the counts at each combination of the factor levels, right. And if you try to use this command table xy, this will give you an output in the form of a contingency table with absolute frequencies. And similarly if you try to divide this table by the length command, then it will return a contingency table with relative frequencies. Now, in case if you want to find out the marginal frequencies, then there is a command here add margins, ADDMARGINS, and this command add margins is used along with that table command, and this gives us the marginal frequencies to the contingency table that was constructed by the command table. So, the entire command to obtain or to add the marginal frequencies in the contingency table will become add margins, and inside the argument try to tell adding margin to what. So, add margins to the contingency table which was provided by the command table xy. And in case if you want to obtain the marginal frequencies in terms of relative frequencies, then you simply try to use this add margins command inside the argument, and inside that argument try to write down the contingency table of which you want to obtain the marginal relative frequencies. Okay, so now I try to take a very simple example and I try to convert the given data into a contingency table, and then I would try to obtain the marginal frequencies. Suppose there are 20 persons and they have been divided in 3 categories with respect to their age. as a child, young person and elder person, and all of them were given a drink and the taste of the drink was asked. You may note here that this is a similar example which I took in the earlier lecture, in the last lecture, where I took 100 persons. But my objective here is to show you that how the contingency table is constructed from the raw data. So, showing you here 100 observation is more difficult. So, that is why I am taking here only 20 observations. So, you can see here that there are 20 persons 1 to 10 and then here 11 to 20, and first person is a child and the child has been asked that how is the drink and he responds good. Similarly, the second person is a young person who said the drink is good. Similarly, the third person is an elder person who said the drink is bad, and then the fourth person is a child who said that the drink is bad, and so on. And this is how we have collected the data on the age and the taste here, right. So, now you see I would try to store this data into two data vectors. One is here person, in which I would try to store the data set which is here this and here this. So, I have simply typed it, and then in the second variable which is here taste, here I have collected the data on this thing good, bad and so on, and this data has been assigned to these vectors in the same order. Same order means if you try to say here first person here is child and this child said that the taste is good, you can see here, and now if you try to see here in the data vector, this is the thing here, child is saying the taste is good and so on. So, these observations are written exactly in the same order as in the table. And now after this I have to use the command table, and inside the arguments person separated by comma taste, and this command will provide a contingency table with an absolute frequency. And when I try to execute this command on the R console, I get here a table like this one. So, now how to interpret this table and how to read this table, that is more important to learn. You can see here one variable here is taste and another variable here is person, and this person has three categories, child, elder person and young person, and these categories are the same what you have denoted in the data. And similarly, the taste is also divided into two categories, bad and good, and this classification has been done by the R software automatically by counting that how many persons are in which category. Now, this is showing you here, for example, if you try to see, this is here your contingency table data or the frequencies. So, these values are your absolute frequencies. For example, this 2 is indicating that there are 2 children which are saying the taste is bad, and similarly if you try to see here, I will use a different color pen, say here 6. So, 6 means that there are 6 elder person who are saying the taste is good, and similarly if you try to take another data here, say here 2. So, this 2 is indicating that there are 2 young persons out of 20 who are saying that the taste is bad. Now, next we would like to obtain the marginal frequencies. So, you can see here I am using here the command add margins, and inside the argument I am using the same command which was obtained here to get this contingency table. Now, you can see here this contingency table is the same which is obtained here, but now there is one more column and one more row which is added in this case here. You can see here this is here sum and sum. So, what is this sum? This value here is 4. You can see here this has been obtained by 2 plus 2 is equal to 4, and similarly if you see here 10, this is here 4 plus 6 is equal to 10, and similarly if you say here this 6, this 6 is here 2 plus 4 is equal to 6, and similarly, if you try to take here this first column 2 plus 4 plus 2, this is equal to here 8, and similarly for the second column, if you try to add 2 plus 6 plus 4, this is here 12. So, you can see here this sum is indicating the marginal frequencies. So, these are the based on row, and similarly here this is the marginal frequencies based on columns. And finally, this value here 20, this 20 is the sum of all the observations or sum of all the frequencies. Which frequencies? 2 plus 2 plus 4 plus 6 plus 2 plus 4, which is equal to 20. So, this is how we are going to obtain the table with marginal frequencies. Now, this is here the screenshot which I will show you that how I have obtained on the R console. Now, we try to find out the same thing with respect to the relative frequencies. In order to find out the contingency table with the relative frequencies, first we need to find out the total number of observations. In order to find out the total number of observations, we have two options. Since we have got here two variables, one is here person and another here is taste, and you observe that both these variables have got 20 observation. So, now I can use here the syntax length of the person, or I can also use here length of taste. Both are going to give us the same values because both the variables have got the same number of observations. So, once I try to operate here the command length of this vector, I will get here a value here 20, which is indicating the total number of observation. Now, in order to find out the contingency table, I have to use the same command, but now I have to divide it by the length of the data vector. So, I try to use here the same command table person taste, and now it is divided by length of the data vector. And once you try to do it, you will get here an outcome like this one. So, first let me try to show you that how you are getting this value. So, suppose if I take here this value here 0.1, how it is coming? If you try to see here in the earlier slide, we had obtained the frequency here, this here 2, which is corresponding to bad taste and child, right. So, now this 2 is being divided by the total number of observations, which is here 20, and this will be equal to here 1 upon 10, and which is equal to here 0.1, and this is here the same value. So, this is nothing but your Nij upon n, which was your equal to 2 upon here 20, which is equal to 0.1. And similarly, if you try to find out here how this value has been obtained, 0.3. So, you can see here the corresponding value here is 6. So, I try to use here say here Nij upon here n, which is equal to here 6 upon 20, and this comes out to be could be here 3 upon 10, which is equal to here 0.3. So, this is how all other values in this table are obtained. Now, in case if I also want to find out the marginal relative frequencies, so I have to use here the command add margins, and I have to use the same command which I have used to find out the contingency table. And in case if you try to do it, you can see here this part here, this is the same as this part here, because this is corresponding to the contingency table. And now there is additional row and column here, which are here like this, and here this. So, the first question comes, what are these additional rows and columns are indicating? So, I will try to show you here that suppose if I try to take here the first row. So, for the sum of first row, which is 0.1 plus 0.1 is equal to 0.2, and this is indicated here in the first value in this column. Similarly, if you try to add here 0.2 plus 0.3, which is equal to here 0.5. So, this is the second value, and similarly the third value here is 0.1 plus 0.2, which is equal to here 0.3. So, they give us the values of marginal relative frequencies. Similarly, if you try to look into the columns, so if I try to sum here these things, so 0.1 plus 0.2 plus 0.1, this is being given here as a 0.4. And similarly, in the second column, 0.1 plus 0.3 plus 0.2 in this direction, this is giving us the value 0.6. Right. So, these two values here 0.4 and 0.6, they are also the marginal relative frequencies. And this is here the screenshot of the operations which are to be done on the R console. Now, before going further, let me try to show you all these operations on the R console. So, I will try to take the same example and I will try to enter the same data set and I will try to obtain the contingency tables with respect to the absolute frequencies as well as with respect to the relative frequencies. So, you can see here, first I will try to create these two data vectors here on the R console, and similarly I try to create this data vector taste. So, you can see here now I have the data on person and here taste, right. Okay, I clear the screen and I try to now create here the contingency table. So, you can see here, this is here the person and here taste. This is the same table what you have obtained. Now, I just want to show you that if you try to interchange person and taste. So, first I try to give inside the argument taste and then person. You see what happens. So, obviously, the data will remain the same, but only the rows and columns are interchanged, that you can observe here. So, in case if I want to find out the marginal frequency of anyone, say person comma taste, you can see here this is obtained here like this. So, this is the same thing what we have just obtained. Now, I try to find out the same contingency table with respect to the relative frequencies. So, you can see here I am trying to take here the same command, but now I am trying to divide it by the length of the data vector and I am choosing here the data vector to be person. And you can see here that we have got here this type of command, and these are the values which are the same which we have shown you on the slides. And now, in case if I want to find out the same contingency table with respect to the length of another data vector, so I try to choose here the data vector taste instead of here person, and you will see here that in both the cases you are going to get the same command, because length of the two data vectors here is the same, which is here 20, right. And now, in case if I want to add the marginal relative frequencies, so I have to use the same command, but I have to add here one command, add margins. So, you can see here that this gives us this value, right. So, you can see here now the sum of all the marginal relative frequencies is coming out to be here 1, right, and this is the same output which I had shown you on the screens. So, you can see here that finding out such contingency table with respect to absolute frequencies or relative frequencies is not difficult once you have some data set. And Now I would try to discuss one more new topic. So now I am going to discuss a tool which is called as Chi-square statistics. And the role of this Chi-square statistics is that it tries to give us an idea by quantifying the degree of association. Similar to what we had in the case of continuous variable, we had correlation coefficient. Right. So one thing you have to keep in mind that when I am going to introduce the chi-square statistics, actually this chi-square statistics is used for testing of hypothesis. And chi-square statistics is based on a probability density function which is called as chi-square probability density function. And when we try to use this statistic, there are certain conditions in the case of test of hypothesis. For example, the cell frequency should be greater than 5 and so on. But here you see I am taking an artificial example. So in this example means I have kept the frequencies to be low, means if you have more data then obviously these frequencies are going to be higher. So while computing the statistics on the R software, you may get sort of warning, but you need not to worry for these things. You have to follow essentially the procedure and the concept. So this chi-square statistics, or this is called as Pearson's chi-squared statistics. This symbol here chi, this is a Greek letter which is written here like this, chi. And this statistics, chi-squared statistics is used to measure the association between the variables in a contingency table. Suppose there are two variables. So the chi-squared statistics for a K cross L contingency table what we have created earlier is given by this quantity. You can see here this is the summation over all the observations, and in the numerator this is Nij minus Ni plus N plus j divided by here N whole square, and divided by a similar quantity Ni plus into N plus j divided by here N. So you can recall that this Nij is giving you the value of absolute frequency, and this Ni plus and N plus j, they are the marginal frequencies of x and y, and small n here is the total number of observation or the total frequency. So this is the statistics which gives us an idea about the degree of association, and this value of chi-square lies between 0 and n into minimum value between k and l minus 1. Minimum value k and l means whatever is the minimum value out of k and l, this can be k or l, whosoever is minimum. Now what is the interpretation of this statistics? Now given the data one can compute this statistics. Now in case if the values of chi-square are coming close to 0, or the value of chi-square is very close to 0, this will indicate that the association between the two variables is weak. So a value of chi-square close to 0 indicates a weak association between the two variables x and y. And similarly you can see here that chi-square has the limits 0 and here this minimum k l minus 1 into n. So in case if the value of chi-square is close to the second limit, which is n into minimum of k l minus 1, then this would indicate a strong association between the two variables. Remember this thing, this is not between like 0 or 1 or minus 1 or 1, something like this. So this value depends on the size of the contingency table. Size of the contingency table. Well, that's a drawback, and that was overcome in some further modification that we are going to discuss. Now in case if you are getting any other value of chi-square which is not close to 0 or this interval n into minimum of k l minus 1, then suitably that will indicate the degree of association between the two variables, say as low, moderate, or say high in general. One aspect of this chi-square statistics is that it is symmetric. Symmetric means that which of the variables you are taking in the row or say column, this will not make any difference. For example, you had seen that we had constructed the frequency table with persons and taste and person. Both the cases this chi-square statistics will remain the same. Now let me just give a particular example which is more popular. Say in case if I have only 2 by 2 contingency table. So suppose there are a variable x and y which have got two classes each, x1, x2 and y1, y2, and the absolute frequencies in these cells are A, B, C and D, which I have written in green color. And now if you try to find out the sum of rows, which is the marginal frequency, this will come out to A plus B, and similarly the marginal frequency of the second row corresponding to x2 is C plus D, and similarly the marginal frequency with respect to the first column is A plus C, and the marginal frequency with respect to the second column y2 is B plus D. In this case, if you try to substitute all the values inside this chi-square statistic, this will simplify to this thing, where obviously n is equal to A plus B plus C plus D, which is indicating the total frequency. Or right. Okay. Now after this, what I will do is the following, that I will take a simple example based on this 2 cross 2 data, and I will try to compute this chi-square statistics, and later on I will introduce some more statistics. And then I will try to measure the degree of association in the same example using different statistics. So this data is about that a sample of 100 students was collected, and they were judged whether they are weak in academics or good in academics, they are good in studies or bad in studies based on their academic performance. Now after this, a group of students was given a tuition, and after the tuition they were judged once again, and the idea was that we wanted to know whether this tuition is going to be helpful or not, whether this tuition means extra studies are really helping the students in improving their academic performance. That is the question which I would like to know on the basis of given sample of data. So what we have done here, that this sample of 100 students is divided into two groups, weak and strong in academics, and some of the students from say weak and strong both, they are given tuition, and after that their academic performance was judged, and after this the data was compiled in the following contingency table here. So you can see here there are weak students and there are strong students, and students who were given the tuition or they were not given the tuition. So it was found finally that there are 30 weak students who were given the tuition, and there were 10 strong students, 10 good students who were also given the tuition. Similarly, there were 20 weak students who were not given the tuition, and there were 40 strong students who were not given the tuition. And based on that, we would like to find whether there is any association between tuition and the academic strength of the students. So we try to find out their marginal frequency. So you can see here marginal frequencies are here, 30 plus 10 is equal to 40, 20 plus 40 is equal to 60, and similarly 30 plus 20 is equal to 50, and 10 plus 40 is equal to 50, and the total sum here is 100. Based on that, I try to substitute all these values of frequencies in terms of ABCD, what we have done here in this table, and I try to use the same formula here, and I try to compute this value. This value of chi-square comes out to be 16.66. This is a manual calculation, right? And then the value of the upper limit, which is n into minimum of KL minus 1. So you can see here the value of n here is 100, and the k here is 2, and L here is 2. The minimum value between 2 and 2 is 1. So 2 minus 1 is 1, and this value here is 100. So now you can see here whether this value 16.6 is close to 0 or close to 100. This is what we have to see, and based on that we have to take a call what's really happening. So you can see here that this chi-square value is not close to 0, but on the other hand it is also not close to 100, right? So, one may conclude that well, there can be a moderate association or a lower association. It depends on you how you want to interpret it. There is no hard and fast rule to decide what is low and what is moderate and what is strong. But yeah, in my opinion, I can say that well, there is a moderate association. Now, I try to take the same example which I had considered earlier, and I would try to find out the chi-square statistics. So, this is the same example which I just considered, right, in which we have collected the data on 20 persons, and their responses for the taste of a drink are recorded based on the category of the age, that is child, young person or elder person. So, you have already done this job, that you had obtained the contingency table here using the command table person.taste. Now, in order to obtain this chi-square statistics, I am giving you here two things. One is the command and second is the application on this example. So, the command here you can see here is CHISQ.TEST. So, this is a short form of chi-square test, and you can see here that inside the argument I am trying to give the data in terms of contingency table. So, this is table comma person comma taste and this bracket closed. This is the same command which is given here. Now, after this I am using here a command $, which is given on your keyboard, and after this I have to write down STATISTIC statistic, and this will give you this outcome. So, the outcome looks like this, that this is showing that the value of chi squared, which is written here as say x, because chi is a Greek letter. So, in R we cannot type the Greek letter. This value is coming out to be 0.277 and so on. But here you will see that there is also a warning message that and it is saying that in chi-square test this data, the chi-squared approximation may be incorrect. Why this is happening? I just informed you that the chi-square statistics which we have used here to find out the association between the two variables persons and taste, this is actually used for test of hypothesis and to test the hypothesis that whether there is a significant association between the two variables, say here in this case persons and taste. So, when we try to apply the chi-square test of hypothesis, then there are certain conditions for the applicability of the test, and one of the condition is that each and every frequency should be greater than 5. And here you can see here in this case there are several frequencies which are not greater than 5, like as 2, 2, 4, 2 and 4, and that is why this outcome is given here in terms of warning, and the chi-square test is telling you, well, you are trying to find out the chi-square statistic, but the number of frequencies are smaller than 5. So, that means the values may not be so accurate and you may have a wrong conclusion, but that is related to the test of hypothesis, and here our objective is very simple. I just want to show you how to calculate the chi-square statistic. Means I can take a bigger data also, but then you will not be able to match what R is doing and what you can obtain manually. Rather, my request will be you try to take the same example and try to create the same contingency table yourself and try to compute this chi-square value. This will come out to be the same. So, now let us try to see that how you can compute these things on the R software, on the R console. So, you may see here that I already have this data on person, we just used it, taste, and here like this, and if you try to create here a table, say here person and taste, you get here the same contingency table, right. So, I try to clear the screen so that you can see everything clearly, and now I try to compute the chi-square statistics. So, you can see here I just use the same command what I have used in the slides, and this is giving you the same outcome. Okay, now let us come back to our slides. Now you see, by looking at the value of chi-square, you can judge whether the association between the academic performance and the tuition is significant or not, right, just by computing the values of n into minimum of KL minus 1 and so on. But now I would try to address another aspect. You can see here in this case you need to compute the values of the range. Well, one is 0, but another is n into minimum of KL minus 1. So, the value itself is not giving you a clear cut indication. For example, if you remember in the case of say correlation coefficient, that was lying between -1 and +1, or the magnitude will lie between 0 and 1. So, just by looking at the value of R, you can very easily communicate whether the association is high or low and so on. So, here a modification was suggested in the chi-square statistics, and a new statistics which is a modified version of the chi-square statistics was defined as Kramer's V statistics. And in this case what happened, that in the case of this Kramer V statistics, the range, since the range of the Pearson chi statistic depends on the sample size and the size of the contingency table. So, these values depends on the situation, that what is the number of row, what is the number of column and so on. So, this issue was solved and a modified version of the Pearson chi-square statistics were presented as Kramer's V statistics for a K cross L contingency table, for the same table. And this was defined as say square root of the chi-square value which we have just obtained, and it was divided by the limit of this chi-square statistics n into minimum of KL minus 1. And the advantage of this V statistics was that it lies between 0 and 1. So, now making inference about the degree of association became more simpler. For example, we can conclude that if the value of V is close to 0, that would simply indicate the low association between the variables, and in case if the value of V is close to 1, then this will indicate the high association between the variables. And similarly, if you have any other value say between 0 and 1, then depending on the magnitude of the value, that would indicate whether there has been a moderate association or a lower association or a strong association. So, now you can see here that in the earlier case we had obtained the value of chi-square to be here 16.66, and we had concluded that the association is moderate. So, now for the same example I try to compute this value. So, using the value of chi-square to be 16.66, I try to compute the value of V statistics, and this comes out to be 0.40. So, that would indicate once again that ideally V should lie between 0 and 1, but it is lying somewhere in the middle. So, I can say that there is a moderate association. And similarly, if you want to compute this V statistics in the R software, for that we need a special package which is called as LSR. So, first we need to install this package by using the command install.packages, and inside the argument within the double quotes you have to write LSR, and once you do it, the package will be installed. I am not showing you here because I discuss it in the starting lectures, and after that you need to load the library by using the command library inside the argument LSR. And if you see what we had obtained earlier in this data set, this example where we had 20% who responded for the taste of drink. So, I am going to calculate this value for this thing. So, remember one thing, I am taking here two examples. One I am trying to do manually, and another I am trying to do on the basis of R software, right. So, this is an example which we had just done on the R software. So, we had obtained here this type of contingency table, and now I would try to compute the value of Kramer's V statistics. So, once again I would try to show you here two things, what is the command and what is the interpretation. So, you can see here the command here is Kramer's V, CRAMERS, and V is in capital letters, that you have to remember. And then I have to give the contingency table for which I would like to compute the value of Kramer's V statistics. And once I do it, this gives me the value 0.11, right. And yeah, once again you will see here the warning message. This warning message is coming out because of the same reason that this is based on the chi-square statistics, and the total number of frequencies in every cell you can see here, they are say smaller than 5, like as 2, 2, 4 and so on, right. So, this is how you can do it, and this is the screenshot, but I would like to show you it on the R console also. So, first I try to load the library. I already have installed this package on my computer. So, I simply have to load it, and after that I will try to use the command here Kramer's V, and inside the arguments I have to give the contingency table of for which we want to compute it. So, you can see here this is coming out to be like this, right. Okay, so you can see it is not difficult at all, and it is more easy to interpret because all the values are going to lie between 0 and 1. So, by looking at the value of say here 0.11, one can conclude here or here that the association is there, but it is quite low, right. So, the taste is not much depending on the age. Now, after this there is another coefficient which is used to measure the degree of association in such a case, and this is actually the called as contingency coefficient, and this is simply the corrected version of the Pearson's contingency coefficient, which is based on the chi-square statistics once again. And this contingency coefficient C, which I am denoting here as a CORR, which is an abbreviation for corrected. This is defined as C upon C max, where C is given by square root of chi square divided by chi square plus n, and C max is given by this quantity, that is the square root of minimum of KL minus 1 divided by minimum of KL. And this statistics also has an advantage that it is lying between 0 and 1. So, it is more convenient to take conclusions or statistical inference using the value which lies between 0 and 1. So, this also have similar interpretations, like as value of C, if it is close to 0, that would indicate a lower association between the two variables. In case if the value of C is close to 1, this is going to indicate a higher association between the two variables, and other values of C between 0 and 1, they would try to equitably indicate the degree of association between the two variables. And now, in case if I try to take this example just for your remembrance, this students versus tuition, where we have found the value of here chi square to be 16.66. Now, for the same thing I would like to find out this contingency coefficient. So, you can see here from this value I was concluding that there is a moderate association. Then I used this Kramer's V statistics, this is also indicating the moderate association, and now let me see what happens in the case of this contingency coefficient. So, if I try to compute the value of C based on the values of chi square equal to 16.66, then the value of C is coming out to be 0.38, obviously n is here 100, and the value of C max is coming out to be here 0.71, and finally the value of contingency coefficient C is coming out to be 0.54. So, since this value is lying between 0 and 1, so this value 0.54 is lying somewhere in the middle of 0 and 1. So, once again I can say that this is indicating a moderate association between the two variables. Now, we have considered different types of things, different types of measures to find out the degree of association between the two variables, where the variables are in the form of counting data. Well, you can see here that different statistics, they are giving us different values and they have got different interpretations. But then obviously, I personally believe that if there is an association present inside the data, then ideally all the statistics should indicate the same thing. There can be a small difference. For example, Kramer's V statistics is close to 0.46, whereas this contingency coefficient is giving 0.56 and so on. But definitely they are indicating, yes, that there is a moderate association. So this is how we go. Now definitely the question comes how to decide whether this is really low, moderate or strong. For that you have to use your own judgment, and this type of power to judge that you can very easily develop by practice. So I would request you, please try to take some more example and try to practice it. Now I would like to stop with this topic of measuring the association between different types of variable, either they are continuous, ranked observation or this counting observation. And you also have learnt that how to compute them on the basis of the given software. So the main thing is this: if you understand the concept, it is easy to compute them, but the main thing comes how to interpret them. So the main objective which you have to emphasize here is this: how to choose the right tool and how to compute it correctly, and then how to take the correct statistical inferences out of that. So you practice and learn this technique, develop this technique, and I will see you in the next lecture. Till then, goodbye.